Assalamu alaikum, my dear students. Here is your teacher Muhammad Ikram. Today we will start with the new chapter, uh, electromagnetism. It would be our lecture number 17. So I welcome you all into my today lecture. Let us start with the name of Allah Almighty. First, uh, the first let me introduce to you that what is electromagnetism. Then we will start as usual. Electromagnetism is in fact what electromagnetism is in fact the magnetic it is the magnetic effect of a current, right? In this chapter, we will study the magnetic effect of a current. But I just want to take you back into your grade 10 level for a moment where you just studies this effect. If you remember, most probably it was, I think, 1826, and the man was Oersted. He was a Dutch professor of physics and the University of Copenhagen, and he was demonstrating to his students the relation between electricity and magnetism. And this effect happens all of a sudden. Actually, he was proving something else to his student. What he was playing, he played that although there is much similarities between the magnetic force and the electrostatic force, as we have studied, the magnetic force and the electrostatic force. The electrostatic force. Electrostatic force is a field force. This is what? It is a field force. Similarly, magnetic force is also a field force, right? It exchanges through field. It acts at a distance. In the same way, electrostatic force is both attractive and repulsive. And the same is the case with the magnetic force also, attractive as well as repulsive. It is due to the interaction of the fields between two charged particles. The positive charge and the negative charge, right? And here, of course, the North Pole and the South Pole. But about the charge, or what is the electric charge, I introduced to you with this in my very earliest lecture. But what are the poles? Poles are the end points of the magnets where the effect is stronger. In the same way as electric field line starts from the positive charge and ends at the negative charge, radially drawn outward for the positive and inward for the negative charge. Here, the magnetic field lines, what is the magnetic field? I'm going to tell you. Here the here the magnetic field line starts from North Pole, as you see, and ends at the South Pole. Inside the magnet, these lines are from south to north, making a closed loop or path. One difference which he was explaining is the existence of a magnet with a single pole. As charges exist separate, charges can exist separate, poles do not, right? Monopole magnet does not exist. A magnet with a single pole does not exist. If you take a magnet and if you cut it into trillion pieces, each piece will still have two poles, the north and the south. And this is your grade 6 or 7 physics, where you can easily learn why they are called the north and the south pole. And it is all because in the reference of the earth magnetic field, which has south magnetic south at geographic north and geographic magnetic north at geographic south. This is why whenever you suspend a magnet freely, it always align itself in the earth north south direction, right? So he was teaching this thing that although these very close similarities, they do not uh, depends on each other, or there is no association between electricity and magnetism. These are completely different aspects of nature, and this is what Oersted was performing to his students. And nature has something different for us. Oersted proved wrong during his experiment, and a strange thing happens. There occurred to be a relationship between current and magnetism, and actually he was showing no relationship. And that was the day when the magnetic effect of the current was discovered. And I would like to tell you that this was actually the first birthday of the electric motor since then, because this effect is used in the principle of the electric motor. So this is how the magnetic effect of the current was discovered, and this is why we are studying the electromagnetism here. And that was the very brief history of magnetism, right? The electromagnetism, sorry, not magnetism. Magnetism is even the oldest science. And if you just look to your book, maybe there might be a little bit history of the magnetism also, that how it was discovered. And most probably it was the kind of mineral rock called the lodestone, which were having the this magnetic effect, that the lodestone was found to attract the iron or other magnetic substances towards itself, right? But they okay, but here we are not likely to study the permanent magnet, right? So let us start with the first topic, and the first topic is magnetic field. Magnetic field. Now, just like a class 10 level or grade 10 level, here I I can just say you that the area or the region around a magnet or a current carrying conductor where the magnetic field acts, or sorry, where the magnetic force acts is called the magnetic field. But I would, for your level, I would like to tell you that magnetic field is in fact the magnetic influence. It is what? It is the magnetic influence. It is the magnetic influence on a magnetized material. Magnetized material, even if the material are permanent magnet or if they are magnetic substances. So magnetic influence on the magnetized material, and B, the on the moving charges. On what? On the moving charges. Why on the moving charges? Because if you remember your class 10, there I told you that moving charges constitutes magnetic field around them. What? Moving charges constitute moving charges constitutes magnetic field around them, or there is what, there is associated magnetic field around current carrying conductor, carrying current carrying conductor, right? There are two important points which I want to tell you. That is the direction and the magnitude of that magnetic field. We usually denote the magnetic field strength called the magnetic induction by B. Now let us see this current carrying conductor. As you see, look here, the if you connect the two ends of the wire, let me say the bare copper wire, with one positive terminal of the battery and other with a negative terminal of the battery, right? Okay, and if you introduce, like here is switch or key, like this one. Okay, so if you close the key, then what will happen? The current will begins to flow in a conductor in a direction is shown to you, and there establish magnetic field around this current carrying conductor. Most importantly, the direction of the magnetic field is perpendicular to the plane containing current, right? These are the moving charges and they constitute magnetic field around them. Once you stop the current, the magnetic field disappears, right? So it is associated what with the moving charges. Now if you have a permanent magnet or another current carrying conductor, and when you bring these two together, then they will influence each other, and that is called the magnetic field, right? That magnetic field influence magnetic material or the moving charges. Okay, now let's see the moving charges, the direction of which perpendicular to be. Okay, they cannot influence them if the charges are moving parallel to the magnetic field. You see, look, there is no magnetic field in the direction of the current. The plane of the magnetic field is perpendicular to the plane of current. Current is in the vertical direction, magnetic field will be in the horizontal direction. Okay, if the current is in the horizontal, magnetic field will be in the vertical direction, right? There is no magnetic field in the direction of the current, right? If you increase the current, magnetic field increases, right? The magnetic field is stronger near the conductor and weaker as you move away from the conductor. It also depends on the property of the medium the surrounding the conductor. So in the same way as electrostatic force is medium dependent, therefore this force is also medium dependent. Okay, so that is all about the magnetic field, and magnetic field is a vector quantity. The direction of for the straight current carrying conductor, the direction of the magnetic field can be found by using the right hand rule, right? If you curls your finger in a way that the thumb is perpendicular to the curl finger, then if the thumb points in the direction of the current, then the finger will That is, the direction of the curl finger will shows the direction of the magnetic field in this case, which is indeed anti-clockwise, right? They are what? They are anti-clockwise. It is just the same as that is every point on the circle acts like a tiny magnet. They acts like what? They acts like a tiny magnet. It is just like as someone have what? The magnet, this is north pole, south pole, as someone have placed the magnet all around the conductor, the quantum magnetic field. Here you can see the magnetic, here you can feel the effect of the magnetic field, but you cannot see the magnet physically. The effect is only there, and it is all because of what? It is all because of the moving charges. If you reverse the direction of the current, then the direction of the magnetic field also reverses. So that is all about the magnetic field. Now let us move on to the next topic. Our next topic is the force on the current carrying conductor. I think yes, current due to current carrying conductor, I told the magnetic field, I did it, and current sorry, this is, I'm so sorry class, this is not current, this is magnetic field. Okay, magnetic field due to current carrying conductor. Okay, the next topic is the force on current carrying conductor. Force on current carrying, force on current carrying conductor. Force on what? Current carrying conductor. Now let us see that in the diagram, as you see, look, if we have the, in this diagram, we have what? We have the magnet, as you see in the magnetic field, you see shown here like this, and it is from north pole towards what? Towards the south pole of the magnet. This is indeed the south pole of the magnet, right? South, magnetic south. Now you see there is a current carrying conductor placed inside the magnetic field. The current carrying conductor, whenever a current carrying conductor, a current carrying conductor is placed inside uniform magnetic field, it experiences a mechanical force. I call it a mechanical force because it moves the conductor, right? You can just say it experiences a force. That force could be a mechanical force as shown in the diagram. Two things are important. One, the magnitude of the force. Magnitude of the force. And second, direction of the force. Direction of the force. Right? First, we just want to know that in which direction that this force will act. So the direction of the force is perpendicular, and the direction of the force is perpendicular to the plane containing what? To the plane containing B and I. are B and L, where what is L? L is the length of the conductor, and the length of the conductor, which is important for us, is the one inside the magnetic field. Okay, this portion will only experience a mechanical force because of the magnetic field, right? So it is perpendicular to what? It is perpendicular to the plane of what? To the plane of the current, as well as what? As well as the plane of the magnetic field, right? This can be found by using the Fleming left hand rule or the right hand palm rule. So if you stretch the finger of your left hand in such a way, if like just like this, see here, let me do it. Look, if it is just like this, and if this, see, if this is the first finger, right? If this is the thumb, and if this is the second finger, right, then the first finger will always be in the direction of the field, magnetic field. In the direction of what? In the direction of the magnetic field. The second finger, it will point in the direction of the current. Then indeed thumb will be in the direction of the thrust produced by this effect. That is that mechanical force, right? And you see all are at right angle to each other, okay, for the maximum effect. So the direction can be found by using the Fleming left hand rule. If you want to use the right hand palm rule, then okay, let us do that too. Very easy. That is, for example, if this is your right hand, these are, for example, finger. Oh my God, very poor drawing. Like this, and then this, then this, like this, and then like this, as you see. So you see here the that here the finger will point in the sorry, this is the direction of what? The direction of the magnetic field B. The thumb in the direction of the current, then the palm, right, it will be the direction of what? The direction of the force. That is a unit vector perpendicular to what? To the palm, right? So the palm will always points in the direction of what? It will points in the direction of the magnetic field, right? A vector perpendicular to it will points in the direction of the force, sorry, not magnetic field, to the direction of the force. So this is how you can use the right hand palm rule. So one thing is very clear, that whether it is the right hand rule or whether it is the left hand rule, it doesn't have anything with the physics. Okay, it can only, you can use this just simply to find the direction, right? There are no such laws in physics, they are just for remembering the direction, right? Understand? Now let us come to the magnitude part now. So here you see, if you apply the right hand rule here on this magnetic field, this is the diagram from your book. Here the magnetic field is what? Into the paper, the cross shows into the paper, right? And the current is in this direction, right? As you see, this is a current carrying conductor, and we use conventional current direction for the positive charges. Then look, the thumb points, that is in the direction of what? Sorry, the direction of the force is shown. So if you apply the Fleming left hand rule just like this here as they have done, then you can find the direction of the force. The magnitude of the force, experiment shows that the magnitude of this mechanical force F is directly proportional to the strength of the magnetic field. This force is directly proportional to the current that is flowing through the conductor, and it is directly proportional to the length of the conductor inside the magnetic field. Remember, not the entire length, only which is inside the magnetic field. And another important relationship is that it is directly proportional to the sine of the angle between I and B, or between between L and B, because I is scalar by quantity. So better to the, if I take the length of the conductor as a kind of displacement, then that is best. Okay, so what does this means? That this force is directly proportional to what? It is directly proportional to BIL sine theta. Experiment shows that the constant of proportionality is 1. I directly omit and write is Bell sine theta, right? This is what the magnitude, right? And it means that beside B, beside I, beside L, it depends on the orientation of this also. For example, if you rotate the conductor right in the horizontal plane by 90 degree, then what will happen? I will become parallel to B, and soon you get this force becomes zero. So the conductor will experience no mechanical force if the current flows in the direction of the B. But as you change the orientation again from angle 0 to 90 degree, from 0 to 90 degree, then what happens? F increases from what? From 0 to maximum. Okay, so you must remember that there is what? That there is no that there is no magnetic force on the conductor if it is parallel to the magnetic field. So you see here, look, for certain value of the angle here, right? Look the length of the conductor as you see here. It makes certain angle with what? With the B. And if this is this one, then the required angle will be, if we take the angle with the positive x-axis, so like theta, like this. Okay, similarly here the force is what? The force is maximum. Why? Because the length of the conductor or the current I, it is perpendicular to the field, and here it experiences no force. Why? Because theta is 0 degree. It is maximum because theta is 90 degree. It is between max and minimum because theta is greater than 0 degree. Theta is what? Theta is greater than 0 degree but less than 90 degree, right? So therefore it lies between maximum and minimum. So this is what the force on the current carrying conductor inside uniform magnetic field. For sine theta equals 1, then you just remember that this force equals by magnitude as Bell. It is equal to as what? This force is equal to Bell, right? From this we can get B as what? B as force F into IL, right? And the SI unit, this will help us, this equation, to find the unit for the B. The SI unit of the magnetic induction, or this magnetic field strength B, the SI unit is what? Tesla. Its SI unit is what? Tesla, such that 1 Tesla is equal to Newton per ampere per meter. All right, that is, the magnetic induction is said to be 1 Tesla. F1, that is F1 ampere of current through 1 meter conductor. When the length of the conductor is 1 meter, when it experiences a mechanical force of 1 Newton, then the magnetic field strength or the magnetic induction is said to be 1 Tesla. So the unit of the magnetic field is what? The unit of the magnetic field strength is what? It is 1 Newton per ampere per meter. This is usually known, this B, it, it is called what? Magnetic induction, but I just call it magnetic field strength. Okay. So this is what? This is the magnetic induction. Sometimes it can also be called the magnetic flux density or magnetic flux density. We can call it the magnetic flux density also. Okay, now this equation, since this is of higher grade physics, so in vector form, how we can express this in the vector form. So of course in the vector form we can write like this equation is how this in the vector form, this can be written as f, I as being scalar, and we will write L cross B, right? So again you can find the direction of this force by using what? The Fleming left hand rule, and the direction of this force is perpendicular to the plane containing L cross B. So that is all about the force on current carrying conductor. Okay, let us move on to the next topic. Now, what is our next topic? Our next topic is the magnetic flux. Magnetic flux. Like electric flux, we have the magnetic flux also, and we can define the magnetic flux as the magnetic flux is defined as it is the dot product, it is the dot product of the magnetic induction B, the dot product of the magnetic induction, the dot product of the magnetic induction B and the area vector A of which the magnetic field lines passes, of which what? The magnetic field line passes. So mathematically the magnetic flux equals B dot A, or simply we can write this magnetic flux B as BA cos theta, where theta is the angle between the magnetic field B or the magnetic induction B and the area vector A. Here it can be demonstrated here like this magnetic flux, it can be max, this magnetic flux can be 0, and this magnetic flux can be negative also, right? And this look, so here you see, look at this thing here. If let us, we have what? We have this area as you see like this, the area, the plane is horizontal, and you see that the area vector is, the area vector is what? The area vector, the area vector for this area vector, its area vector is what? The area vector of the plane, this one, the for this area. Now you see that, look, what is the magnetic flux? The magnetic field lines as they pass through this area. Now you see that the direction of this is what? The tangent vector to the unit tangent vector to the flux, right? Now flux passes through, as you see, through the plane of the area. Here you see, look, what this is that angle which I told you between B and what? Between B and A. If this area is what? Increasing, then what happens? The flux becomes 0. And here, look, what you see here, that you do not observe any flux in this direction. There is no magnetic field lines in this direction. Why? Because that if you just see, look, if this is A and if this is B, and oh my God, like this. Okay, so if you just take it like B in this direction, okay, and if your area is still this one, for example, making it like this, then what is this angle? 90 degree, and cos of 90 is 0, so you don't observe any magnetic flux in this direction. So the flux ib in this direction is what? 0. And purely in this direction for this point, okay, the magnetic flux, that is, you see the area vector is parallel. And if the area vector parallel to what? It is parallel to B, and what happens that the flux is maximum. It is what? It is max. Right here you see, look, it is this situation where you see the flux is maximum line pass through. Here, this is when the theta lies less than, that is the theta less than 0 and greater than or equal, greater than 90 degree. So it is between minimum and maximum. This situation demonstrates this. Here, it is this situation, just like the this one diagram as you see, right? So this is what? This is the magnetic flux. The SI unit of the magnetic flux B dot A, RBA cos theta. The SI unit of the magnetic flux is Weber, such that one Weber equals, what is this unit of this? The unit of this is Tesla, and if you know what is 1 Tesla, Newton per ampere per meter, Newton per ampere per meter. And what is the area? The unit meter square. So what does this mean? That 1 Weber is in fact Newton meter per ampere. So very simple, even we can say joule per ampere also, like this. So 1 Weber is equal to this, right? This is the SI unit of magnetic flux. Also, from this we can, from the definition of this flux pi b BA, we can get the magnetic induction like this, B by A. Okay, and what is it? That is the, we call this as the magnetic flux density. Magnetic flux density. This is what? This is the magnetic flux density. So magnetic flux per unit area. And this magnetic flux density, it is unit Weber per meter square. It is what? It is the Weber per meter square, right? It is what? It is Weber per meter square. I'm sorry, there is no E in it. I'm used to this stupid thing. Weber. It is Weber. Okay. There is, here I wrote correct. Clear? So this is all about what? The magnetic flux density. So magnetic induction, magnetic flux density, they are the same. Another important point which I want to share with you beside this, that there are other unit for the magnetic flux density or magnetic induction also. One is, I told that it is Tesla for B, where I wrote here. Okay, that is, I told that it is Tesla. So this, beside this, there is another unit also. Okay, and we call that gas, right? I just remind. And 1 gas equal 10 to the power minus 4 Tesla. Okay, or 1 Tesla is 10 raised to the power 4 gas. So that is all about today lecture. So inshallah, see you in the next lecture. The most important topic there will be, I think, the ampere law. So inshallah, see you there.